It's recording. Let's go. Today's lesson, moving away from indices and we're moving into logarithms. Let's test your transformations again. Let's go. Let's start off with Noah. What does D do to the logarithmic graph? Vertical translation, very good. Vert translation. What does A do to the graph? Can I please have, let's go with Tyler. What does A do to the log of graph? It is dilation. Of factor what? Can I please have Rango?
Dilation of factor n. Dilation of factor A from the x-axis.
Very good. It's affecting your y value, so it's moving away from the x-axis. So dilation of factor A from the x. What does the C do? Can I please have, let's go with Mia. Horizontal translation. Very good. Horizontal translation. And then what does the N do? Can I please have Ryan?
Dilation of 1 over n from y.
Very good. Factor of 1 on n from y. Very good. Out of them all, what are we missing? We've got a dilation, we've got translation, and I'm missing reflection. Obviously, A can also have the reflection as well. And also N could also have a reflection as well. What type of reflection is A? Can I please have Albert? Reflection in? The x-axis. Is that right? Vertical flip. Yes, that is correct. Reflect in x. Therefore, this is reflect in y. Okay, so that's chapter 3. Let's look at some properties. Here's your log graph. That's your basic log graph. The one I drew here is log base 2 of x. We can see there is a vertical asymptote. Okay, so kind of like your exponential, we have a horizontal asymptote for an exponential graph. Then now the inverse will have a vertical asymptote. Okay, so instead of y equals 0, it's x equals 0. And instead of y-intercept being 0, 1, we now have x-intercept as 1, 0. So everything's reflected. Okay? So let's fill in the details. Log graphs have a domain of, what's the domain? So going back to chapter 1, exercise 1a. Joe, what's the domain of this log graph? What would you say?
0 exclusive to infinity. Exclusive.
0 to infinity, inclusive of 0 or no?
Exclusive.
Exclusive. Very good. Or you can use, as you said, R plus. Very good, because that does not include 0. So when you use R plus, it does not have inclusive of 0. If you want to include 0, you have to use the union and the braces to say include 0. Okay, so be careful. R plus means 0 to infinity, not including 0. What is my range? Can I please have Tara? R, very good. Can be any value. Okay, so hence any vertical translation does not affect the range, but your horizontal translations can affect your domain. So that's what you have to be careful of. So that means vertical asymptote is key. We've got a vertical asymptote at x equals 0. Make sure to label that in. Vertical asymptote at x equals 0. One other thing that to note, log graphs do not exist. Thanks, team. When x is less than 0. Why? So I can't do, what I'm saying here is I can't do log e of negative 3. I'll do 2 just to make it easier. Why can't I do log base e of negative 3? That is correct. On the graph, we can definitely see that it only goes closer to 0 but never equals to 0, and also can never have a negative. But I'm sort of looking from what you understood from exponentials. What is log 2 of negative 3 as an exponential or indices? Very good. So if you reread this, this is the same thing as saying 2 to the power of what will equal to negative 3. That's what log is. Log is to find the power. So when you read that, just think about it. 2 to the power of anything. If you square it, it just keeps getting larger. If you want to get negative, the smaller the value, still, it only gets smaller and never gets to 0. That's why it's impossible to find 2 to the power of something to equal negative 3, which also means log 2 of negative 3 is impossible to find. Okay? So that's got to be one of the things that you need to check. When you're doing your exam questions, you'll get an answer. Sometimes the answers, you have to sub it back into the equation to check, does it equal to a negative? Because if it equals negative, it means it's impossible. Yeah? Which I think I have one of the examples later for you to check out. All right, and then it will always have an x-intercept. Yes, we know. Let's go down, 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 down. This is the inverse. So it is a reflection. So 2 to the x. And log base 2 of x is a reflection in the line y equals x. That should be it for the first page. That's it. Okay, so just knowing your e2 to the x, and this is log base 2 of x. Let's do some examples now. Going to the next page, flip over. Let's read some transformations. I'm going to pick a few other students now. Question A says, determine the transformation required for the graph to go from log 2 of x to f of x. So it means read the transformation. Part A, let's do Dr. T, which means I want the dilation, reflection, then translation. So give me a dilation, if you can see it. Can I please have, let's go with Adrian. Looking at the question, give me a dilation that you can see. Okay, so there's a 2. So that is a dilation factor because you're timing to the log. So dilation of factor 2 from? Very good, because you're affecting your y value. So it's moving away from the x-axis. So from the x-axis. Very good. Give me another dilation. Can I please have Ian? Beautiful. So that's 3 over here. That's 3 that's multiplied to the x there. That's a dilation factor as well. But remember, this is affecting the x. And it is the reciprocal, so it's actually dilation of factor 1 over 3 from the y, because you're affecting the x value, so it's moving away from the y-axis. Very good. Let's get to reflection. Do I have a reflection? Name one if you can see it. Let's go with Serena. Reflection in the x-axis. Yes, I can see that too. It is right here. That's the negative, which affects the y value, so reflection in the x-axis. Do I have a reflection in the y-axis? Let's go with Charlotte. Do I have a reflection in the y-axis? Yes or no? Yes, we do. Thanks, team. We got a negative in front of the x there, so yes, there is a reflection in the y-axis as well. And then now, the easier parts, translation. What kind of translation can you see? Let's go with Samuel. What translation can you see? You've got 2 up. Very good. We've got a plus 2 there. So it is translation of 2 up, or 2, positive 2 in the direction of the y-axis. And what else do I also have? I do have a translation, another translation, which is a bit trickier. What is this translation, Ringo?
It's negative 6 on the x-axis. If you reorder it, it'd be negative 3x plus 6. But that always, like, am I wrong?
Yes. One of the ways to one of the ways to read it, if it helps you, factorize it. Find the coefficient and then find what's not the coefficient. So you got negative 3x plus 6, which you were correct. Factorize it. Take out the common factor, and that's your dilation. So if you take it out, negative 3 as a common factor, you get what's inside the brackets? Yeah, x minus 2. So what does that mean? This is a reflection. That's still the dilation of 1/3, but that tells you the translation. Okay, so if you're having troubles with sort of reading it, you can factorize it to see. That tells you straight away you've got the minus 2, which really means to the right by 2. Okay, so translation of 2 to the right. the way I teach to my year 11s, which is different to you guys because I haven't taught them transformations, I normally just tell them, let 6 minus 3x equal to 0, solve for x, and whatever x equals to, if it's positive, moves to the right, if it's negative, moves to the left. Okay, so if you do it that way, moves to the right by 2. Okay? All right, team. Next one. Thanks, boys. Part B. Determine the asymptote domain and axis intercept. So here we can see that there is 2 to the right. That will affect the domain. So we got x equals 3. Don't do what I just did. You should use a ruler when you're doing the asymptote. Make sure to use a ruler. Whoops. 2. My bad. Whoops. Should be a dotted line, shouldn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. X equals 2. So 2 to the right. And is it reflected? Yes, it's reflected in the x-axis. So it normally looks like this. So it flips upside down. But it also has a reflection in the y-axis as well. So we can expect it to look something like this. What I don't know is where the x and y-intercept is. So I got the shape, but for all I know, it could actually look like that. Okay, so what you need to now do is to make sure to find the x and y intercepts, if there are any. In our case, it obviously will have a y-intercept and have an x-intercept, so let's solve for it. Y-intercept is the easiest to find. So here we go. Y-intercept is when you let x equal to 0. Let's solve for it. Y will equal to, or f of 0 is equal to negative 2 times log base 2 of 6 take away pretty much 0 plus 2. Negative 2 log 2 of 6 plus 2. Can we solve that? Maybe not. If you can't solve it, then you leave it as an exact value. So it would be, I'm just thinking, no, I can't see it. You just leave your y-intercept then. So your y-intercept, now you have to sort of guess, is this, yep. If I factor the negative 2, what do we get? Oh, is that what you're asking? When you're doing y-intercepts, probably not. If it was a function, yeah. If it was an actual equation of the function, then yes, factorize it. Otherwise, leave your answer as is, an exact value. Okay, so in this case here, looks like we aren't 100% sure whether this is going to be a positive or a negative value yet, but you can kind of guess it. Do you think this is going to end up being a positive value or a negative y value? How do you know? Let's do a bit of a guess. So if you read log 2 of 6, means 2 to the power of what will give you 6, roughly? 2 point something. So let's just say 2 point something times 2, or negative 2. So that's a negative 4. Negative 4 plus the 2 gives you roughly? Negative number. Very good. So do an estimate. So even if you don't know it, you can kind of guess it. We just know this is a negative value. Okay, so we know that the y-intercept is a negative. So far my first graph kind of looks relatively correct. X-intercept. Let's work out x-intercept. X-intercept occurs when y is equal to 0. So you get 0 is equal to negative 2 log base 2 of 6 minus 3x plus 2. Let's do it. Inverse operations. Minus 2 on both sides. And you get, oh, it's lagging, equals negative 2 log 2 of 6 minus 3x. Divide both sides by negative 2. You get 1 is equal to log base 2, 6 minus 3x. All right, I'm going to pause here. So what do you do now? Trying to solve for x. So all I did was I subtracted 2 on both sides, then divide both sides by negative 2, and I got a positive 1. Very good. The other idea is how do you get rid of log base 2? The opposite of log base 2 is exponential base 2. So I can do 2 to the power of the right-hand side and then 2 to the power of the left-hand side. That essentially gives me 2 equals 6 minus 3x. Okay, so these are inverses of one another, and 2 to the power of 1 is just 2. Add 3x on both sides. If it's easier for you, subtract 2 on both sides, and you get 6 take away 2. Yep. This one. So this step here, I'm just going to rub this part again. To get rid of a log, you got to do the inverse of log. So log base 2, the inverse of that is exponential base 2. So doing exponential base 2 means like you've got a 2 to the power of something. So I do 2 to the power of whatever's on the right side, and then 2 to the power of whatever's on the left side. These two are inverses, so they'll cancel out. And then whatever's left over comes here. 2 to the power of 1 is 2. And then that removes the log. Okay? All right, then from this step here, 3x equals to 4, and x equals to 4 on 3. So far, it doesn't look too bad. It looks about right. So you got 4 and 3 is less than 2, so that's correct. 0, 4 and 3, 0. Y-intercept is when 0, and you've got this massive number, negative 2 log 2 of 6 plus 2. And you got your asymptote. Sketch the graph and the domain. All right. Let's finish off the question. Shh. Thanks, team. Let's finish off the question. From the graph, you can already see the domain, the range should be all real values, and the domain should be negative infinity up until 2. Not inclusive. Okay, so this is an example of what you'll be doing. Thanks, team. Please don't speak while I'm speaking. I find it highly disrespectful that you feel the need to speak exactly at the time that I'm speaking. You could wait till I finish and then you can speak. But to choose to speak while I'm speaking is a direct sort of conversation saying, I don't really care what you have to say, which I assume that's not what you mean. All right. That was as a fluency skill of what you need to know with logs and exponentials. It's about solving algebra and sketching. The last part of this, question 6 and question 7, is a bit different. So I thought I'd choose it just so that you have an idea of how to solve this. So I'll do 6 so that you can do 7 on your own, yeah? Have a look at this question here. Find the transformation that takes the graph of y equals 3 to the x to the graph of y equals e to the x. There's a bit of a trick here, and it uses the property that I gave to you in the previous notes. Has anyone done this type of question before? Hands up if you have an idea of how to do. Dante. Okay, thank you. Let's just pause there. Let's think about what Dante was thinking at the moment. You're trying to figure out an original equation, which is 3 to the x, that maps to the new equation, which is e to the x. True? What's the problem? The bases are different, so it's hard to compare to see the transformation. So one of the first steps you should be trying to do is, can I rewrite a base 3 so that I have a base e? That's what you're trying to do. What we know is one of the properties that, like I said before, how do you get rid of logs? It's the inverse, right? So inverse of log is exponential base. Then the inverse of exponential base is log. So here, if I wanted a base e, then I would need to have e to the power of log e. These two will cancel out. What do I need? This 3 to the x can be written as e to the log e of 3 to the x. Can you see what I'm doing there? Because these two are inverses of one another. 3 to the x is this. If these two cancel out, you end up with 3 to the x. Why did Dante say log e3 of x? Where'd that x come from? Using rule number 3, we can bring the power down. And what's nice about it is this is the same thing as writing 3 to the x is the same thing as writing e to the log e of 3. If you bring the x to the front, it's x times that. But we normally like to write the numbers first at the front so you can see which one's the dilation. So here it's e to the log e of 3 multiplied to x. Now, if you compare this to the new equation, which is what you want, you can work out the transformations. They both have a base e. This is clearly a dilation. But remember, original y, original x. So here's your original y. Here's your original x. This is your new y, your new x. And if we did the transformation mapping technique, original y is equal to new y. So that's one way. But then if you look at the x's, let's highlight it. This is what I'm substituting. New x is equivalent to log e of 3 times x. So if I write that down, new x is equivalent to log e of 3 times x. This is my dilation factor. Okay, it doesn't have to be a number. If it was 3x, you would have said dilation factor 3 from the y-axis. Yeah? In this case, you would say the dilation of factor log e of 3 from the y-axis. So here's the dilation of factor log e 3 from y-axis. Where's the confusion, or where's the part that you guys might take a bit of time to sort of try to understand, is this bit. The 3 to the x is still here. Okay, I'm just rewriting it in terms of a property that e was what I wanted. So e to the power of log e, I know those are going to cancel out, and this is what's going to be left over. So these two are the same. So when you say 3 to the x, that's equivalent to you saying e to the log e of 3 to the x. That's what I'm saying. Okay, and that little trick of using that property, we know these cancel out, so technically these two are equivalent. That's how we can read the dilation factor. Question 7 is the same. If you're having a look at that, have a think. Later on when you're doing exercise 5e, have a look at question 7 from your textbook. That's another one for you to practice with this idea. Okay? All right. That's pretty much 5e. Let's move on to 5f. Okay, so 5f is then reading the equation. But that 5e, last bit there, that 5e question 6, 7, it's a bit of a rare one. It's just trying to teach you how to use that property. Okay, just this property here. All right? Most of 5e is about this. It's about you sketching properties, domain, range. That's what 5e is. This one's just a trick. Cool? All right, flip over to exercise 5f. Here we go, last part of today. Well, I'm going to finish this video actually.